Professor Penninger, thank you very much for taking the time to do this interview with me. You are one of the leading immunologists and genetical engineers, one of the top scientists of our time, and you've had a very unique and impressive career, taking you from a small village in Upper Austria to your current position as the director of the Life Science Institute of the University of British Columbia in Canada. From 2002 to 2018, you founded and led the Institute of Molecular Biotechnology of the Academy of Science of Austria, with whom you still cooperate. You've published an incredible amount of studies in the top scientific magazines. You've been awarded with innumerable international prizes, and the research and the findings you and your team have succeeded in have led to breakthrough and revolutionary therapies against, for instance, osteoporosis, and also to substantially understand the mechanisms of cancer. Currently, you are working on a drug, a therapy that may alleviate severe cases of the disease COVID-19. How does it feel like to have ventured on this remarkable journey?
First, thanks so much for your nice introduction. The father of chaos theory, Ilya Prigozhin, actually once wrote he can mathematically calculate the lives of people, because, you know, we have all these bifurcations we have to take. And I think he would have had a hard time to calculate my bifurcations from the village to actually sitting here. So I never got an idea, you know, having a shower or have this eureka moment. So, you know, it's all built on listening to others, listening to ideas, knowing the field we are researching, asking the right questions, and then really, you know, and then be doggedly going after it. In my case, it happens, I'm listening to people, things ferment, and all of a sudden, I think I have an idea. 90% of my ideas are total nonsense, but sometimes they actually work.
Many of your ideas do work. According to your peers, you spill out ideas at a rate second to none. What drives you? What keeps you motivated? And what role does competition and collaboration play in the world of science? You've left Austria and Europe initially at a young age to build and establish your career in North America. So in balance, how do these two continents compare according to your experiences?
Yeah, actually, when I was young, I just graduated from medical school. I had the luck to move to Toronto and learn my business and be exposed to the best of American science. And of course, in America, you learn, you know, you just do, you know, there are many ideas, and, you know, and you can think about them for a long time, or you can just actually go for it. And if you have the tools of science, you know, how to ask the right question, how to use most modern technologies to ask the question, then you can actually have impact in multiple fields. And I was also very lucky early on. I remember, because, you know, when you're a young scientist, you protect your ideas because you think this is, you know, this make your career and nobody should take it from you, because, you know, to get to your question on collaboration or being protective, protectionism of ideas. And I have to say, initially I was very protective of my ideas. And then I had once the luck to have dinner with Oliver's missus. Oliver's at that time actually developed gene targeting, genetic engineering of animals, and he won the Nobel Prize. So it just came off of winning the Nobel Prize, and here I was, this little village from Austria, talking to the recently awarded Nobel Prize winner. We talked exactly about this topic, and he gave me the most amazing answer, which I teach everybody, all my students, all the people who work with me. And he said, if you talk to 10 people, 2 people will steal your idea, but 8 people will give you a much better idea.
So that's a very good advice, I think, not only in the realm of science, but in any other realms. People are always very worried to have their ideas stolen, but in actual fact, it's collaborating with others, which builds to the real results, if I'm interpreting that correctly.
Exactly. There are always some people who will steal from you, but who cares? Because
Well,
if everyone,
it must be hard
Life, yeah,
sometimes, but anyway. One of the big questions that we always pose ourselves in Europe is why there's such a great brain drain out of Europe. Whereas I think every country within the European Union, at least, wants to keep the brilliant minds that each country basically has. But something in the structure, something in the mentality lacks. What would your suggestions be from a political point of view to keep the talent within Europe and to build up a very, very important counterpart with a group of scientists that stay and are based in Europe?
yeah, Europe has some really good examples to actually bring talent to Europe. Max Planck Institutes, for instance, I'm a university in the UK, Copenhagen. So I think there are also some very good examples we can follow. Of course, the North American business model, the Canadian, the US business model was always to bring the best talents to the countries and let them loose and then create a structure where they can actually stay in your country, allow them to immigrate, to stay there, give them careers. And if you actually analyze the data of the most successful, economically most successful places in the US, it's actually the places where the immigrants are. And this was, of course, always the business model. Bring in the best talents, let them loose, create a structure where they can stay, so they start new companies, the ideas are just flourishing, and to create this culture. So often in Europe, we have these borders down, or sometimes worried about, people coming from somewhere else, taking our jobs away. So that's not very helpful. So I think in this regard, not in all regards, but in this regards, we can learn a lot from the US.
So basically freedom, open-mindedness, and openness towards other cultures, other ideas, and thinking beyond sort of your little world.
Yes, and of course the structure, the hierarchical structures they've set up in North America, these department structures where everybody is the same. So, if you have a department of immunology with 50 people and 25 of them got the job because of nepotism, it's fine because the other 25 don't care. And as a scientist, it's my business. So what I did, is my glory, not for somebody else's glory. And in Europe, unfortunately, many structures are set up. There's a big professor running departments, people for a long time before they actually get to the top. And then, so I don't think it's a very helpful structure. And I've seen it because we here in Vienna, the institute I developed, we introduced a North American structure, totally flat hierarchies. The young researchers are completely independent. Many other institutes in Europe do the same, so it's not totally unique. But I've seen how well this works. It's actually very simple. You hire the best people, create a structure where they can work, you protect them, allow them to think out of the box, and then magic things can happen.
So it's also a question of mentorship and listening to scientists, young scientists who haven't maybe already a certain position, but whose ideas could be very stimulating and could bring new fields and new findings. What is the role of financing, of money, of the support of big pharma industries? How would you rate that in Europe versus, let's say, North America?
I think in North America it's better. So in Europe, there are some big farmers in Europe. They sit in Switzerland or in Germany, some in France, of course, Sanofi in UK. But many of them actually doing the research in Boston now. So Boston somehow, even the Japanese, one of the big Japanese companies closed all the research in Japan and they all do it now in Boston. So that's what one sees, because they're brilliant universities, lots of talents around, the people you can hire, so that they tend to cluster. And in Europe, in some countries, this is happening. Denmark is a really good example how it can work. Apparently, if actually after Brexit, if you then look at university rankings, best university in Europe, if there are no Swiss universities and no UK universities.
No British universities anymore. Okay.
Exactly, it's actually Copenhagen. So,
but so actually you have to break up the encrusted structures in Europe and become more wider. That's your advice, basically.
Yes. Having said this, there are some good structures, as I said, the European Research Council, for instance, how they finance innovation, I think is actually a really good example. So there are also examples in Europe which have really worked, and actually where the others are jealous. The North Americans would love to have an ERC council. Because, I can tell you the reality in Canada is every researcher is struggling from one public funding to the next one. The grants with right people in my institute now I run in Vancouver spent half a year just writing proposals to get money to research, and that's crazy if you think about this. And the success rates in Canada are now 14–15%. So this means.
But once you're in a position such as yours, does it become easier to get the support you need to do really groundbreaking work?
Partially, not always. So trust me. I went back to North America because here I was actually in a place where we had lots of money, we could do lots of things, could be very innovative. Now I'm back to real life in North America, from one public money to the next. And the first grant proposals I wrote, scientific proposal, they were all killed. So I'm back to reality.
But I have to say that's quite a, how shall I say, that's quite nice for us mortals to know that also the great scientists sometimes have failures and build upon these failures.
No, absolutely. And I think, these 4 years of Donald Trump were just an aberration. So the American universities are just very strong institutions with lots of clever people. So.
You have also founded several companies with laboratories, and one of those companies is based on your findings, or let's say is working on a therapy based on your findings at the end of the 90s, beginning of the 2000s. And I'm coming to our current health crisis, which where you had researched on the ACE receptors and their implications, and on the way the SARS, the SARS-1 virus would dock onto these receptors, which is now of imminent interest in the development of a new therapy to alleviate severe cases of COVID.
Yeah, so many years ago, actually, my group, my laboratory in Toronto at this time, co-discovered ACE2, angiotensin converting enzyme number 2. And we published lots of papers that ACE2 protects from organ damage in the heart, in the kidney, in the vascular system. And then it turned out that ACE2 is the receptor, the entry gate for the SARS virus, 2003. And we actually contributed some of the most fundamental data to this. We had the first data showing without ACE2, there's no infection. We could actually, at the fundamental level, explain why the SARS virus became a killer virus, because it docks onto its door ACE2, actually get rid of the door, but the door is required also to protect our lungs and many other tissues. So this virus did not just use ACE2 to infect us, but the infection led to a loss of tissue protection via one of our most fundamental systems in physiology and medicine. So people really like this, even won prizes on molecular explanation for SARS infections. But then, of course, the SARS virus disappeared and nobody cared about this work anymore. And now ACE2 turned out to be the entry gate for the second SARS virus causing COVID-19, and it was catapulted more or less into the heart of the pandemic, being now the most researched protein on the planet. And probably more than 90% of all vaccine efforts and also medicine developments of new medicines actually homing onto this interaction of the virus with ACE2 to block this interaction. Because if we can block this with vaccines or with medicines, then the virus cannot enter our cells anymore. And of course, if it cannot infect us, then there will be no COVID-19. So that's the fundamental principle. And this is what we actually have been doing over the last months now. Also work which started really 15 years ago. We're making a soluble form of this door, a soluble of ACE2. And basically it does two things. It catches away the virus from the real door. So it works like something we call a molecular decoy. And it protects the tissues. And so this is what we've been doing. And the clinical study, phase 2B clinical study in severe COVID-19 patients has just finished recruiting. And if everything works in February, we should know if it works well, which we all hope, and the science tell us it should work. But of course, we have to test it carefully, or if it doesn't work. So
well, I think all our hope is focused on this worldwide. I have a question for this. We've all been a little bit frightened about the mutations in the virus, which we've been hearing on the one hand in Denmark with the minks, but most of all recently in Great Britain. The virus, I don't know if it's become more aggressive, but it's become more contagious as far as I understand. Has this got any implication on the therapy that you've been now researching and developing?
So not on our therapy, because even if the virus mutates, and we know it mutates, it always did mutate, it does not mutate at the rate like the flu virus, but it does mutate. Now around 12,000 mutations already of the virus. So the scary part on this virus, which just emerged in southern England, is it has actually carried 17 mutations at the same time, one of which is actually allows the virus to bind to ACE2 much more. So
it does.
And this is probably, that's why it's contagious, because of course, if you can, go through the door you need to infect us much easier than, then you don't need to be a scientist to understand that this is more contagious virus. It actually, this British variant also carries the mutations from the minks. And this was interesting because this mink mutation was scary because it could allow the virus to partially escape from the immune system, so from vaccines and so on. So we are not there yet. So one has to monitor very carefully these mutations. The virus will always mutate. So of course we have to monitor this careful. The vaccines can be adjusted. So maybe it will be like the flu that every year we have new vaccines that can, so we have to monitor it. But now, of course, the beauty of our approach is because the virus cannot mutate itself out of ACE2, because it mutates itself out of ACE2.
That stays a constant.
Exactly, because we cannot get the disease anymore we call COVID-19. So that's why we believe we have a very rational approach, because if the virus has mutations, it cannot bind to ACE2. There will be no COVID-19, because that's the entry gate giving, this particular symptom and spread of the virus. So that's why we believe vis-a-vis all the efforts being made in the world, that our medicine has a place there.
What is difficult to understand for someone who's not a scientist is, or at least for me, I understand these ACE receptors. We all have them. What I don't understand is why does the illness have such severe effects on some of us and hardly any on the others when we all have the same receptors in us? Does one know?
I would love to give you an answer. I have no idea.
I would love it as well.
No idea.
Actually, this is still not really understandable for nobody.
No.
Do we all have the same amounts of ACE receptors? Because as far as I understood, younger people, children, have less, which is maybe
Correct.
one of the explanations why they can get infected, but the symptoms aren't very severe in
Correct.
those cases.
And I heard reports the new variant in UK apparently makes more younger people and kids sick, which of course makes sense, because if it can dock better to ACE2, even if there are less of them, but then
they still, which actually comes to the controversy which has been debated, I think, all around the world. At least I know it has in Austria. Should schools stay open or not? And there's a balance to be made between your right to be educated, but also the very real danger of the children, even if they're not very symptomatic, to spread it in the wider population. What is your stance on that?
My stance are the data. And the data, initially everybody believed kids cannot get it, which is not true. So kids can get it. They just get much less severe disease. Some of them can actually get very severe disease, this multi-inflammatory syndrome, but much less than if an 80-year-old person gets it.
But they can spread it.
They can get it and they can spread it. So if you ask me, to have the soft lockdowns where the schools are open, they were probably breeding grounds for the virus.
Very clear answer. Thank you very much. Your field of expertise is obviously also vaccines. And even if you haven't actually developed one, what is your analysis of the vaccines which have now been released and which are currently being already administered in the States, but also in Europe, two of which are based on a very new technology called messenger RNA. The others, such as AstraZeneca and the ones in Russia and also in China, are based more on traditional vector systems. How would you evaluate them? Which, if any, vaccine would you give the preference to?
Most of them actually have the same principle. They show our immune system in different ways, the spike protein from the virus, and our immune system reacts and makes antibodies and T cells, which then would kill infected cells. So that's why ACE2 and this interaction, actually 95% probably of the vaccines, try to turn on our immune system to block this interaction between ACE2 and spike. So that's the principle. In one way you can do this with messenger RNA, another way you put the genetic information, the vector like AstraZeneca or the Chinese do. But the principle is very similar. So I would not have a particular preference. Of course, there might be small differences in side effect profiles because, an adenovirus vector is different to nanoparticles being used to deliver this genetic information. But first, this doesn't change our genes. Some people are worried that this is actually, this information of the virus and it can reprogram genes. So there's no worry about this.
Some people think we're all going to be guided or controlled by Bill Gates, which maybe is not a real problem.
But not in that sense, no, not in this sense.
You have an incredible number of findings that you made in your career. One of them was also the findings on the protein RANKL, which was one of the bases of a therapy against osteoporosis, and is also linked to the development of breast cancer in women. And you have now, and this is very, very recent, released a study where you have, again, which is one of your topics, spoken and researched on the thymus gland, which is also a very important factor in pregnancies in women. Would you be kind enough to reiterate what you have found in your study and in your research?
Yeah, we just published in the journal Nature, and we reported in the journal Nature a completely new function of this organ, which we call thymus. So the thymus is normally the place where T cells are born. That's why we call them T cells, thymus-derived cells. So they have these fundamental functions in immunity. So we actually figured out that the thymus is a second function, which is paradigmatic and has never been reported before. And this is in pregnancy. The thymus responds to female pregnant hormones. And via molecular system, which we call rank ligand and rank, which also controls bone loss, for instance, and lactation, formation of a lactating mammary gland, and actually is involved in breast cancer in females. So sex hormones talk to the thymus in pregnant females via the system rank ligand. This allows the birth of a particular immune cell. And this particular immune cell protects the embryo from being rejected by the mother, which we kind of knew. But the second function was totally new, and this was it actually keeps the mothers metabolically healthy. And with a single mutation in this thymus organ, actually the female mice, so we did experimental genetic engineering in mouse, the female mothers which had this mutation actually all developed diabetes in pregnancy, with very long-term consequences to the offspring. So basically the thymus is not only important to rewire immunity in pregnancy for females, but also keeps them metabolically healthy. So in brief, what we found was a completely new function of an organ we knew for a long time.
Which is the basis for developing medicine which can prevent diabetes during pregnancy, and also the predisposition of diabetes in the children that are born of such women. Is that correct?
We hope so. Of course, now it's a beginning, we're still defining the fundamentals, but of course we need to define the fundamental mechanisms to develop new medicines and new interventions. I am told now, of course, depending on different countries, that around 15% of all pregnancies nowadays in the West, actually the women become overtly diabetic, which has then consequences to the next generation. So this is a huge problem. And at the end of the day, we're all born. This is absolutely critical for the future.
And critical for women. Such as also the findings that we just discussed and that you made on the protein rancor and its connection to, on the one hand, osteoporosis, and on the second, also breast cancer. Could you explain to us, and also the development of an incredible therapy against osteoporosis, which was developed thanks to your findings?
Yes, so this goes back even further than ACE2. ACE2 we discovered in '98, and this we actually worked on even longer. So a friend of mine, Bill Boyle in Los Angeles, actually cloned a molecule which he called osteoprotegerin ligand, which turned out to actually regulate cells which eat bone arrays, so-called osteoclasts. So my group, being a genetic engineer, we made the first genetically mutated animals which lacked rank ligand, so OPG ligand, now we all call this rank ligand. And it turns out it's the master regulator of bone loss. So you have to imagine there are hundreds of reasons of bone loss: old age, sex hormones, inactivity, space flight. There are many reasons for bone loss.
Space flight, okay.
Zero gravity, if you walk a lot, you have actually strong bones because we have mechanosensors with strong bones, and our bones are every 10 years approximately totally remodeled. It's not they're built and they don't. So we permanently change our structures. And there are two cells which do it. One adds a bone and one eats the bone. And the balance between the two cells gives you healthy bones. Old age, for instance, the bone-eating cells become dominant. That's why when we grow older, we lose, which we call, if it's in the whole body, we call osteoporosis. Now, there are many reasons for bone loss. It's like a funnel. You can throw all the reasons in on the top, information, space flight, old age, sex hormones, but all of them need to go through the funnel, which we discovered. The funnel is rank ligand. So, and it has this receptor called rank. Now you can imagine, of course, if you have a medicine to block the funnel, bone loss in many conditions. And this is what we discovered, and an American biotech company developed this. This medicine to block this funnel has been approved. It's actually called Prolia and Xgeva, approved for osteoporosis and people with bone loss and metastasis in cancer, which is a huge problem. So this medicine has been approved. It's actually literally used in millions of people. The company which makes it, I think the annual revenue of 4.6 billion a year.
Yes, I was just going to say, how frustrating is it for a scientist? On the one hand, it makes you probably very happy, and it must be a very good feeling to know you've been able to help so many people around the world. On the other hand, it must be a little bit frustrating to know that you're not really participating in that sort of percentage on the actual profits. Is that hard sometimes? And is that one of the motivations to found your own company as well?
Yeah, it was one of the motivations, but that's how the world works. So this company, I can name it, is Amgen, they allowed me my career. So
so it goes in both directions.
Exactly. Yeah. So without them, I probably wouldn't sit here. So I'm very thankful for them. And it's of course great to know that my discovery made many people millionaires, even if I didn't.
But also that you've saved many people from a lot of pain and illness. In what way?
That's why I studied medicine. That's why I became a medical doctor. Exactly.
Really?
Bottom line.
Well, that's the right motivations. I'm not sure everybody has the same motivations, but
No, because at the end of the day, biotech is a very tricky business. It takes a long time. It's prone to failure. Biomedical research is a very tricky business. Mental failing. You have projects like what we published with this Alzheimer's organ. This was 12 years of work. We didn't publish any year of tough work. So you have to do this for the right reasons. To do this because you believe one day you get rich or win a prize.
It's not going to be,
It's, you're just permanently.
But it's a nice side effect if it happens.
Exactly, but then things happen anyway. But also, when I start companies, I tell the people I work with, we have to do this for the right reasons. And the right reasons are to develop medicines which can help people. The rest will follow, because if the medicines work, if they have now a blockbuster or if it helps 50 people, at the end it doesn't make a difference. If it helps people, and this must be our singular focus, because and it's of course how you make decisions, right? This is fundamental. How you live your vision, what decisions you make, where you put your money. And
I want to open a parenthesis on that, because I find that very interesting. There are obviously illnesses such as breast cancer, which affect so many women in the world nowadays. And your findings has helped to understand how breast cancer develops. But there are illnesses where only a few people, or let's say in comparison, only a few people are affected. How does it work to get research for such illnesses? And I know, and that's why I'm talking about it, that on a specific gene defect, for instance, you and your team are working on developing a cure or a therapy, but it'll be not so widespread. It's not so, let's say, popular. How would you say, what could be good incentives that also for such more rare illnesses, the research is available?
Of course, so if we work with rare disease, first intellectually and medically, very interesting, because actually having 8 billion people and having 25,000 genes, so every gene actually needs to be mutated. So humans are basically our genetic incubator to find out the function of genes. So 10 years ago, we couldn't do this because we had not the technology to read out the genes and the genetic changes in the genes very fast. So now we can with the sequencing methods, and now you can read a whole human genome in 10 minutes. And of course, then we can analyze it. What we started 20 years ago, with animal studies or flies or worm studies to figure out gene functions, we can actually now go straight into humans, right? Because there are variants which give rare diseases. So that's why they're very relevant for medicine. The statins, the drugs being used to lower cholesterol were discovered in a rare disease condition, where people had this condition and they tested medicines and it worked for them. So at first we can learn a lot of them. So I think this should be supported.
So even if it's for a rare disease, the side knowledge which may come up can nevertheless help a great many people as well. So you have both.
Exactly. The huge impact. The reality is, of course, that sometimes this is not really seen, how important this actually is. Actually, a friend of mine runs a very large rare disease foundation in Europe, Care for Reya, of Munich. So I'm part of this group, and we do we have these international networks on rare diseases. So I'm working on this for a long time. But he also said it's very difficult sometimes to get enough funding for children.
Of course, yeah.
Disease. And so yes, there is a problem.
That's a problem.
If we know we can use this knowledge for understanding the world much better, but
then you convince people more.
Exactly. Even for children, research in rare disease, it's often sometimes very difficult to get.
Very difficult. Money plays obviously a very important role in research. It has to, and the pharma industry has a lot of money, but also needs to know that it will get profits as well. And sometimes, as far as I know, therapies are developed that are very, very costly. And the problem is, how can the average person then receive such therapy? Not only in Europe, where we are a wealthy nations, basically, with quite good health systems, but in countries that are less fortunate, people will not have access to therapies that are maybe already available, but just too expensive to get. As a scientist, isn't that painful to see? And what would a solution be? Or is there no solution? Is that just the cynical way our world works?
No, it's very painful to see. Actually, as a young medical doctor, I worked in Africa, so I've seen it. Still remember. So actually on Thursday, we got a lot of medicines from the West. So we had actually everything. Then on Friday morning, the military came in with machine guns into Soloway. And, and I saw kids die of tetanus, measles, and
of treatable diseases, basically.
So I have seen it, to see kids die because you don't have a needle for an injection. That's frustrating. But I think there's some examples where it does work for it. The HIV drugs, for instance, they have been developed in Europe and the US. They're actually miracle drugs, because 30 years ago, getting infected with HIV virus was a death sentence. And now people, they adhere to to taking the drugs, they can have nearly normal lifespan.
Like a chronic illness that they can live with for a long time. Absolutely.
But of course, then of course there are many people in Africa who have got infected and of course don't have the money. But I think what they understand is via the WHO, also drug companies, lots of the drugs, they make money in the West, but they also donate a lot of drugs to Africa. And one of the side effects is that apparently many people actually benefit of the drugs, for instance, in South Africa. Probably not as much as they should, but I think the examples how it could work and how the world could work together, make money here, but use it also for the greater good and donate drugs to people who cannot afford them.
The debates regarding the vaccines, that we in the West can obviously afford all the vaccines, but how do we get them to other countries? And finally, I think in a global world, we can't really think anymore, this is happening there and we're safe, because we saw it with the virus. It just travels everywhere anyway. So
exactly. And it's important
it's in our interest.
And it will come back to us if we don't, don't get it to people who cannot afford it. So we will not. The virus doesn't care how much money we have, how rich we are.
It makes everything, it evens it out. It's an equalizer, basically. I just want to also not forget to talk about other discoveries. And basically also what I think everybody's very interested in is what are the future products and projects and the research you made.
The rank ligand and rank system and its role in breast cancer, because we did this initially. This is also a system how the sex hormones talk to the breast and tell the stem cells to grow and form a, and drive the cells all the time to cell cycles or grow. And of course, if this happens over many years and the mutations, and this is probably one of the initial triggers of breast cancer. So based on all of this, we're actually running now a large prevention study for breast cancer in North America with the NIH and with Harvard in Australia, in many countries in Europe.
So on a very, very large scale.
Yes, these women who have high susceptibility of BRCA1 mutations like LGB. So we're basically running the studies on young women who have this high risk of breast cancer, around 8% lifetime risk to develop breast cancer. So based on our fundamental insights. So we just started the study, but of course, if this works, then we might have an intervention for prevention of breast cancer. So I'm really excited about this. So
well, that's incredible, because I think in the meantime, 1 in 8 women develops breast cancer in the span of her life, which is a lot.
Yeah, and of course, the big breakthroughs in medicine were not always medicines. After you're sick, you get something. But the breakthroughs were, of course,
prevention.
To prevent it. In water, vaccines. So, preventing disease in literally tens of millions of people.
Talking of breast cancer, have your findings also been related in any way to what we call hormone therapy that many women are forced to turn to during the menopause?
Yes, so there are large studies also confirmed now recently. So the 1 million women study, other studies which clearly related hormonal replacement therapy with increased risk of breast cancer. Of course, hormonal replacement therapy is another benefit. They can potentially protect against ovarian and endometrial cancers. It's not a simple correlation, but clearly this has not been shown in studies.
There is a correlation.
The risk of breast cancer. So of course, and the amazing thing was in the studies, the bad sex hormone was actually not estrogen. It was progesterone.
Progesterone.
And progesterone is the sex hormone which turns on rank ligand in the breast to tell the cell to grow. So we have actually molecular explanation why the sex hormones can directly link to breast cancer and how they actually tell the cells to grow, to interfere at this mechanism rather than at the hormonal mechanism. And so if, and that's why we do this clinical study, because, we don't want to shut down the hormones or block them to be given, but go one step further where actually the hormones act to possibly drive the breast cancer. But
isn't it that progesterone also protects from other sexual
cancers? That's why it's complex. So yes. And
so there's not yet a very clear answer. This is okay and this is not okay. It's a very delicate balance between all these.
Then we don't have to interfere with the good part, but we only interfere with the bad part. Exactly the idea why we do this.
You have also worked on findings, as I said, regarding colon cancer, chronic inflammatory bowel diseases, heart failure, lung failure. Where do you stand in all these different points? I mean, it sounds so much that you're saving the world at the moment, where I have the feeling. So many, really, for someone who's not a scientist, it looks as if all these different subjects are so varied and not really related. What's basically the common point? Where do you start? And this is something which I'm personally really interested in, the knockout mice.
That's actually our little secret of success.
Really?
So because we changed and kind of became a genetic engineer. We changed genes in mice and then asked the question, what's the gene function? That's why rare disease interests me, because the nature interferes with gene function and gives us something which we can read out in humans. So that's a massive.
So if nature makes a mistake in the gene sort of pattern, this is where you sort of focus in.
Exactly. So for instance, then there's somebody who doesn't have the right ear. Then we know that's a gene which probably regulates ear development, for instance, only as an example. So that's what we do. And of course, then you realize, it's not, nature is not an expert of one gene does this thing. The next gene does these things. Genes do many things. The holistic, nature is holistic. As an example, rank ligand, one of my favorite genes, regulates bone loss, regulates, expansion of the breast in pregnancy. Now we published it regulates Alzheimer's, regulates many systems. And of course, if you would only study one system in isolation, you would never figure this out. But since we have this knockout mice, the mouse is guiding us because the mouse is showing us. So how we actually found this connection to breast cancer, there was no reason to look for the breast because, you know, we studied bone and we knew rank ligand is essential for bone loss. This was our first paper. And that's it. You know, why do we even come up with the idea that it regulates breast? And we came up with it because when we had a female mouse with this mutation, so they had sex, they wanted to have sex, they had babies, and every baby always died. And then we wondered, why do the babies die? And then it turned out because the mother could not give them any milk. And so started to look in the breast. So this is basically these animals and these studies actually guide us where we should look. And also rare diseases guiding us where we should look. So that's and then of course you realize, you know, if you only study one aspect of rank ligand in the bone, we would miss a lot of fundamental biology and we could actually not understand the entire system. Now we know, you know, because what it emerges now is sex hormones talk to the rank ligand system and tell it to grow a mammary gland, a lactating mammary gland in pregnancy, talk to the bone to release calcium from the bone, so the babies have strong bones, talk to the immune system so the mothers don't reject the baby. So, you know, this picture emerges what it's actually doing. So that's why we work on different systems. So let nature guide us instead of us believing we understand nature. Let nature help us to understand nature.
And as listening to you talk, I think it's not just always the findings, it's basically you ask the right questions.
Yeah, you have to ask the right question and have the right technologies to answer the question. So that's why actually science is always driven very much who has the latest technology. Because fundamentally the question we ask, people asked 40 years ago. But now we have just totally different technologies to answer the questions. So it's actually science at the end of the day is a technology race. Who has the best technologies to answer the same question people asked 40 years ago? So we are not more clever than them. We just have different technologies.
I understand. What about the other points such as heart, lung, bowel diseases? Is that something you are currently still working on?
We still work on. I'm actually very excited. We have some new pathway potentially in heart attacks where we can actually protect the cells from dying. So if this is real, then you know we could develop new medicine against heart attacks. So, but it's still early days, and I'm very excited about the project on Parkinson's disease, which we fell into this, and if this works, we might have hit on the fundamental new mechanisms for Parkinson's disease. And
which is until now an incurable disease.
Yes, and there's this one medicine, L-Dopa, you know, actually in Austrian introduced, Ole Hornikiewicz, who just died last year, and he should have won the Nobel Prize 10 times for this, you know, the only medicine against Parkinson's disease which really works. He introduced this in the 60s. There's no new medicine really, which ever came on the market besides little variations. So I'm very excited about what one of my students is doing. So, but this is also a project we have now 4 or 5 years into, and we have animal models of Parkinson's, and actually when we change the system, we can totally protect them from disease. So let's see.
Where do you see us in 10, 20, 30 years time? How will the science develop? I mean, we're not going to all be immortal, but will our longevity sort of be prolonged? Will we age better and healthier? What are your predictions?
I'm on some European think tank on aging, which I find really interesting. So as we sit here, so our life expectancy is probably 92, 94 years already, which is stunning.
Which is not bad.
Our kids, my kids, you know, who are not around 20, probably their life expectancy will be 95, 96. So just think about this. Has really interesting implications also how we actually will live our lives. So, you know, will we really go to school and go to university and then for the next 60 years have one job? This will change our social fabric also. So is already happening.
Mhm.
Of course, the social fabric has not caught up yet with science, and that will live longer. So this will be interesting. But how if you really look at these three big things which happened in the last 15, 20 years, was really, if we sum it up. So we learned how to read genes. We can read the genetic code of basically every living organism. And we cannot just read it, we can actively change it. So it's really the first time in history of our world that we can actively change genes, which we have always been doing with selective breeding and so on. But now we know we change this one and then something happens. So that's the first thing. Secondly, biology has learned to turn back time, which I find really interesting also from a philosophical principle. Our interview started at a certain time point and will end, and then we all have the experience. This is an hour which passed. So that's what it is. But biology, also was the same idea. We are born, we grow, we age, we die. But now with, of course, the Yamanaka factors and, Yamanaka being able to turn back all cells into stem cells again, this famous pluripotent stem cell, which is also built on actually work from many, many other people. So this was not out of the blue. He just used what other people were using before. But if you fundamentally think about this, we can take your cells or my cells and can make, the primordial cell again. So we can turn back the biological time, which is quite amazing. Of course, the third thing with this, reading genes, changing genes, turning back time, people have learned to grow human organs, little
from stem cells, you mean?
From stem cells, last made the first blood vessels. So people make mini guts, little lungs, little guts. So, we can engineer tissues. And of course, by doing so, understand biology much, much better, human biology, much, much better. So this, I think, these are really big things which happen in the last years. Read and actively change genes, turn back biological time and use the stem cells. I can grow from myself, from a 90-year-old person to grow a little human heart. And that's, of course, I think, and around this, of course, a lot of science has happened.
This all sounds very godlike. Are scientists the new God? And you personally, what is your take on God?
It's simple. I take it with Richard Feynman. In one of his essays, he wrote about this. And so there's a world for moral compass, however we call it, God, philosophy, our social construct we have built up over many centuries. And there's a place for science. Science is not a replacement religion, it's a method. Science is something which we can measure, and therefore science cannot replace the social constructs or moral compasses, or however we call it. And of course, it cannot explain if there's a God or not. And of course, it cannot replace religion, but religion has also no business in science. So science is a method. So I'm a very pragmatic person. And that's, so I think if somebody believes in God, it's their own personal thing, how they want to deal with this. But science is certainly not a replacement for God, because if I know how, the system works, which leads to bone loss, does not make you or me a better person. We just know how bone loss works.
But it makes you a very powerful person.
Potentially. I think biotech and what we learned will, of course, revolutionize totally how we do things on this planet, the medicines we can develop, aging, how we can possibly interfere with things. So I think we are just at the surface. So we will see a lot of amazing things in the next years.
Can it be scary? Does it scare you sometimes, the potential in maybe the wrong hands?
Well, in the Brothers Karamazov, Dostoevsky writes, every stick has two ends, the good end and the bad end. So yes, people
it's part of the same coin.
yes, people will misuse it. There will be always some crazy people out there. There will people use it for the good of the world. So that's how it is. The same with cars, you know. People still die in car accidents and we still accept it. So, I mean, it's a bad example, but yes, it will be misused. I think we should not be naive about this.
But let's believe that the good will outweigh the bad.
Absolutely, and it already does. I mean, just look at the COVID-19 vaccines based on science. You know,
Absolutely.
10 years ago, this would have taken us 5-6 years to make a vaccine like this. So it's spectacular.
Everything is accelerating.
Absolutely. The new medicines against cancer. 10 years ago, melanoma was a death sentence. Now 20-30% of people get healed tumor-free because of new ideas on fundamental understanding of immunity and how we make therapies. Do you see anybody who walks around with crippled hands anymore?
Yeah.
Totally disappeared. 30 years ago, there were many people who had crippled hands because of arthritis, new medicines which totally prevent this. So there was some amazing advances in medicine the last years. It's always too slow because, you know, it's us, we get sick, people get sick. And of course, if it affects us, it's always too slow. But in the grand schemes, I think the progress which has been made is just spectacular.
So we look forward to a brave new world, and we thank you that you make this kind of new world possible. Thank you very, very much for your time, and I wish you lots of success for all your future projects, which is in all our interests. Thank you very much, Professor Penninger.
Thank you so much. And as a last word, you know, it's easy for me to talk, and this talk is based on a team of lots of clever people who work with me. So it's actually teamwork, and the more we work together, the better it is for all of us.
The greatest minds are always the most modest. Thank you very much.